Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight.
Whimsical Wavelengths is here again to show that it's useless to fight gravity. Every time I have, it's brought me down. My background is using gravity to investigate volcanic behavior, movements of mass, and changes of density. Check out episode 12 about Mauna Loa volcano. Today, we're going extraterrestrial, to the cosmos. Let's start with Newton. 2 sentences to try to sum up Newtonian gravity. Every point mass attracts every single other point mass by a force acting along the line, intersecting both points. The force of attraction is proportional to the product of the 2 masses and inversely proportional to the square of the distance between them. Or, if I was going to write this as an equation, the force F equals the gravitational constant times the mass of one object by the mass of the second object divided by the distance between those 2 objects squared. That's the famous equation. And it works really well for nearly all things within our solar system. But there were things it did not fit. Mercury's orbit is one famous example. Newtonian mechanics of gravity gave the wrong prediction for the precession of Mercury's closest point to the Sun. It just couldn't fully predict the orbit. And then Einstein developed a theory of space and time. And it was about time. And it was a leap forward, changing how we viewed the universe and how we could measure it. Einstein's theories of general and special relativity make assumptions, and as such, I guess it's important to state them here. I mean, of course, the assumptions are important, but this is not where I'm trying to go at the moment. Hopefully, one of these days I'll get back to them. But the assumptions are, first, the laws of physics are the same and can be stated in their simplest form for all inertial frames of reference. And 2, the speed of light is a constant, independent of relative motion of the source. It can be argued that this seminal work, together with other Planck's or seminal works about the observations from Hubble on galaxies existing outside the Milky Way, and the fact that our universe is expanding, represent the beginning of the modern age of cosmology. The basis to look at a number of different phenomenon are here because of these seminal works, from black holes to gravitational lenses. Hey, do you know what happened when 2 black holes walked into a bar? Well, the bar collapsed under their mass. Want more? Don't worry, I can keep these jokes accelerating indefinitely. Today, we're going to get into one of those topics directly: gravitational lensing. So much to get to, from invoking Einstein to understanding this phenomenon, and invoking his name again. First, to be fair to history, the idea that light traveling close to a massive object will bend it, which can be accomplished with a lens, like in telescopes and eyeglasses, was first actually postulated by Newtonian mechanics of gravity. And attempts to calculate this light bending due to mass can be found way back in 1801 by John Snowder. Hopefully I'm pronouncing his name right. To get to the modern understanding of gravitational lenses, however, requires Einstein's relativity. The theory explains gravity as a result of distortions in space and time created by mass and energy. Starting to sound like technobabble? Hopefully not yet. Yeah, a physics book is not something you want to drop on your foot. It's a weighty subject. And to get out from that enormous weight, someone has volunteered to come on the podcast. Right here on Whimsical Wavelengths, to get from relativity to gravitational lenses, and to tell the story correctly is hard to do in one episode also. So I've actually planned this one as a pair. So no, it's not time dilation due to a weighty subject. Please welcome Dr. Georgios Vernardos, who got his PhD in astrophysics from the Center for Astrophysics and Supercomputing in Swinburne University of Technology, Melbourne, Australia, and is currently an assistant professor in physics and astronomy at Lehman College. where rate my professor rates him extremely high. Yes, I do my background on every guest that comes in to make sure that they can explain everything better than I can. And it's a real treat to have you here on the podcast.
Thank you for the invitation, Jeff. It's my pleasure to be here, ready to talk about exciting science that I've been doing throughout my career on gravitational lensing and related topics. Very happy to be here.
Yeah, and likewise, I really want to just jump right into the whole science part immediately, but I know patience is a virtue, and my one little paragraph snippet to introduce you does not describe you and your scientific interests very well. It goes way beyond gravitational lenses, I'm sure, but without adding a ton of jargon, can we get a little deeper into it using real simple terms about what your research questions are and why this avenue of investigation speaks to you?
Sure. Gravitational lensing is a phenomenon like many other phenomena in nature. For example, take the prism that Isaac Newton used to play with and others alongside him. Light behaves in a specific way through a prism, and light behaves in a specific way through a gravitational lens. And through what we observe with our telescopes, looking at these gravitational lenses throughout the universe, there is a bunch of things we can learn for nature. For example, things about dark matter, even about dark energy, things about the evolution of galaxies, and of course, as the name suggests, the phenomenon acts as a lens, as a magnifying glass, as a natural telescope, in other words. So it magnifies things that are so far, so distant in the universe, that we were never going to be able to see them with just the telescope on Earth. But with the gravitational lens in front of them, we have a boost in this magnification, so we can see further.
So you're using these phenomena to probe the cosmos more generally, trying to understand everything from mass, dark energy, dark matter, basically a little bit of everything as far as how the universe comes together and its laws.
Right. A little bit of everything. There is way more than what I just summarized in the universe, but yes, luckily, and we're, at least myself and my colleagues are excited about this, gravitational lensing is a phenomenon that can touch upon many fields, many topics of study.
All right. Well, we've got so much to get through and go way beyond just my little bit of intro that has been recorded. And I was reading the paper at the center of today's episode and just kept going like, wait, we can do that? And I quickly realized I only really understood roughly one aspect, and I do mean roughly, of gravitational lensing. And there was just such a wide world out there. To get us there, though, I think we need to start somewhere and maybe perhaps with a brief talk about relativity, perhaps. Is that a good place to start?
Sure, absolutely. This is the right place to start. And as you correctly pointed out, starting with something simple, in quotes, as gravitational lensing described through relativity, we can set the foundation for understanding the wild variations of the phenomenon as it manifests itself across scales, across wavelengths, and so on.
So I guess relativity, though, as I understand it, is the idea, because Newton didn't really talk about space as something that could bend and change its shape. It was, for the lack of a better word, like space was almost linear. You could just kind of draw a line from one side to the other. If it's a straight line, it's a straight line, kind of. I mean, it's a little bit more complicated than that, perhaps, given the intro that he also suggested that we could bend light next to massive objects. But he wasn't really talking about a bending of space and time. But special and general relativity makes that case for gravity, doesn't it? That the bigger the mass, the more warping with space and time.
Right. So the correct picture, let's say, has the following components. Space-time is an analogy to a fabric. You can stretch it, you can put a heavy object on it, and it will create this well, this potential well, this bending, this curvature. This heavy object in the universe, in the actual space-time, is some galaxy, some black hole that creates this bending of space-time. Einstein framed what happens in the universe in the most correct way so far with his general theory of relativity that explains not only ideas about bending of light that were there even before him, even many years before him, actually. It also predicts new phenomena. And the most, let's say, the most wild place where you can have this new phenomenon is right next to a black hole. So there, many weird things happen. Some of them were already perceived and somewhat discussed before Einstein, but with the theory of general relativity and with other scientists after Einstein digging deeper into its details, we learn so many things about black holes and how space-time behaves there. So photons follow straight lines in a flat space-time, but when you have a curvature, a curve, a bend, a potential well in your space-time, they get deflected. They follow straight line, which is actually itself not straight, is in a curved space-time. So black holes are, you wanted to interrupt me?
No, not really. I was just going to make the comment that, it's light always travels in a straight line, but that straight line isn't necessarily straight for the observer.
Exactly. This straight line can exist in a curved space-time. That's the right way to put it. Straight lines in curved space-time are still straight, but also curved, if you want. So black holes are specialists in curving space-time because they have a lot of mass in a very small space, so they're very compact, so they can create extreme, very deep potential wells, very extreme curvature. And photons that pass by a black hole can feel this and start falling into the black hole. So some of the photons either will graze the black hole and escape. Some other photons will fall inside the black hole, never to be seen again. That's the definition of a black hole, right? Some other photons, though, will fall into this potential well, into this curved space-time around the black hole, and they will stay there, rotating, doing funky stuff, rotating like a satellite in orbit around this black hole, until eventually they either escape, they may bump into another photon or some other particle that happens to be there, because black holes are also consuming gas around them. They're feeding by this gas, they're accreting it and growing in mass. So some photons may scatter off, some other of these photons that are in orbit like a satellite around the black hole can fall into the black hole. So there is a very nice picture in popular culture about this, for this phenomenon, from the movie Interstellar. When they visit one of the black holes, the matter around it and the photons are behaving exactly in this way. It's in fact a proper simulation taking into account general relativity and all the orbits of photons properly calculated and so on. So you see this very weirdly deformed and distorted shape of an accretion disk, which is just a donut, a very flat donut around the black hole. But when it's distorted, it's actually lensed by the black hole. These photons are deflected, are lensed into this strange and very charming, very exciting shape. And you notice that I used now the word lensed for the first time, right?
Yeah, I mean, that's where we're going. And I guess I still haven't seen Interstellar. I know that is almost blasphemous, but hopefully those that are listening will view that in a different light, because I definitely have heard multiple times that they did an amazing job with getting certain aspects at least visually correct in the show.
Yes, they did the actual job. They had an astrophysicist, an expert in general relativity in their team, and what you see, the images, are actually supercomputer simulations of what happens around such a black hole. So they are the real thing. They are not animations. They are solving proper equations to get what you see, to simulate it.
Right. Okay. We've been talking about curving of space and time due to mass. I really want to ask about warp speed, but perhaps I'll save that for another time, or at least closer to the end. So let's get into gravitational lensing. Otherwise, we'll never get there. We'll just keep getting deviation stage left constantly. So we need a lens to talk about gravitational lensing, sort of. I mean, it is a lens, but to really understand it, perhaps a step backwards before we can go forwards. Now, typically I'm wearing glasses. I'm here on the podcast. I'm not wearing them because I don't need them to see the computer. I need them to see distance. And a lot of us do, whether it's glasses or contacts in the eyes. And honestly, when it comes to optics, I hardly remember the class. I took it during summer between co-ops, and the lecture was so checked out. I think I need some help here. So let's start with what a normal lens does here on Earth.
You set the field very nicely, because as physicists, and other scientists, of course, we like to think with analogies. And the analogy of a gravitational lens is obviously an optical lens, as you said very nicely, your glasses, or a magnifying glass. Maybe a magnifying glass, it's a slightly better analogy in this case. So what happens is that when you have curved space-time somewhere in space, caused by a black hole, or caused by a galaxy, or caused by something else, we'll come back to the different flavors of lensing a bit later, I hope. Or I imagine.
Absolutely, that's the plan. If we don't get deviated too much, I mean.
Exactly. So what this thing does, it's very similar to an optical lens. You have a source of light. Think that you're in a dark room. Think of the universe as a dark room. You're in a dark room, and you have a little lamp shining somewhere in this room. This lamp is your source. In the case of gravitational lensing, it could be a distant star, or a distant galaxy, or a distant quasar, or a distant gravitational wave even, but we will get to that. So, you're in that dark room, and you have this source of light, and you're looking at it with nothing between blocking the line of sight or interfering with the line of sight between you and that source. So there is no lens in this case, there is no lensing, you see a clear source. As soon as something passes in front, a glass, a piece of glass, a magnifying glass, whatever, you will start seeing the source distorted. It will be deformed a bit. If you have a magnifying glass, it will also be magnified, so it will become much brighter. If you have some fancy contraption made of glass, think of a glass sphere or whatever, a deforming piece of glass, you can really be creative here. You will create many images. You can even create multiple images of that source. In fact, this is what the magnifying glass is doing, but it focuses all these images into your retina, into your eye. So you just see the net effect, which is just an increase in the photons that you receive, that your eye receives. So back to the analogy with the universe. You leave the dark room, now you are in a dark universe, you have a distant galaxy, another galaxy passes in front. So normally you would expect two things that are perfectly in line to block one another, but the galaxy in the front acts as a lens. So it's not blocking the line of sight to the one behind it, it's lensing it around it, magnifying it, distorting it, creating this weird banana shape, images of a background galaxy, and so on. So we see two galaxies. One is the lens that looks normal, and around it, it has something like a halo or a ring. It's actually called an Einstein ring when the alignment is very close to perfect. And this is what we call galaxy-galaxy lensing. It has a special name, strong lensing. It's a very exciting flavor of gravitational lensing, but it's also becoming mainstream quickly because of new discoveries, because of new instruments. But we will get to that, I'm sure.
Well, I mean, that's the reason why we're here to some extent.
Exactly.
All right. So the focal point, which is like the spot where the image comes into focus on a normal lens here on Earth, like my glasses, is dependent on a number of different things, such as thickness. I mean, we've all heard the phrase Coke bottle glasses. Maybe not anymore, actually. I keep dating myself. The curvature of the lens, change that focus so you can see closer or farther. There's also the material itself, which can cause different amounts of refraction or change the color of the individual light that's coming through. Space doesn't have thickness. So how do these lenses and properties compare to gravitational lenses? Like, is it even a lens?
Very nice questions, very to the point. And I'm happy I have the answers for you, or at least where to begin thinking or unraveling this nice package called gravitational lensing. So first, there is one little comment that I wanted to make to link what we said before about black holes to what we are saying now about galaxies. So what happens near the black holes is very extreme compared to what happens when you have a galaxy curving space-time and acting as a lens. The equations that you need to solve around the black hole are very complicated. As soon as you go further away from the black hole, not that far actually, a few times the size of the event horizon, there is a very nice approximation, and it leads you to a very simple equation. Very simple. It's almost the same as Newton's law for gravitational force. This equation gives you the deflection due to gravitational lensing when you are away from the super curved and super wrapped warped space-time around a black hole. So this is what we use for galaxies as well, and for large-scale lensing, basically anything that is not a black hole.
Okay, but what about, is there some way to see what, I might be jumping ahead here, but I'm going to ask it anyway because it's come to my mind. Is there some way to understand or see when a light has gone through a gravitational lens? Because when we have it on an earthbound lens, we know we can even come up with properties and stuff like that. Like, is there like a wavelength shift or something like that as well?
This links to your previous question. So first, a very important difference between optical lenses and gravitational lenses, and this is where our analogy breaks, is that optical lenses are sensitive to the wavelength, like a prism. Prism is a material made of glass. You have electromagnetic waves being deflected, or actually I should have said light being deflected in an electromagnetic way. The phenomenon is very different in its nature. And the deflection that you have depends on the wavelength. That's why you get the different colors. They have different wavelengths. You can separate them because they get deflected at different angles. Gravitational lensing does not behave in this way. It curves space-time, and it doesn't care what type of photon is crossing that curved space-time. It could be a gamma ray photon, so very high frequency, or it could be a radio photon, very low frequency and very high wavelength. So they are all deflected.
Now I got to interrupt. I'm sorry.
Yeah,
I got a question now.
Sure.
You said previously you said gravitational waves, and now we're talking about photons, and we're not even sure gravitational waves have, like, we haven't discovered yet a particle that associates with them. So they also get lensed, right?
Okay, let me...
I know, I just threw a wrench into everything. I'm sorry.
No. So gravitational waves have been observed, and they are being more and more discovered in the last few years, in the last few months. It's another revolution, if you like. Before going to the gravitational waves, which is an extension of what we will talk about, the short answer to what you're asking is yes, gravitational waves propagate through the universe, and they themselves can be lensed by gravitational lenses. It's something that can happen. We haven't observed it yet. I have colleagues who are writing proposals as we speak to ask money to hire students and postdocs. This is 90% of what we do as researchers, to study this phenomenon and study lensed gravitational waves or even micro-lensed gravitational waves. We can go quickly diverge into this unknown territory, but very cutting-edge science, lensed gravitational waves.
Cool. Yeah. I mean, like you said, we've only just recently been able to really start to record these waves in these big, long... One of these days, there's only so many episodes I can get through. One of these days, we'll go through a gravity wave one nice. Day. Okay, back on topic. Sorry, I just couldn't resist. The nature of gravitational lenses, as we've kind of already alluded to, they're big, they're small, they're enormous. So how big of an object does it need to be before we can use it as a gravitational lens? Like, can we use the moon? Can we use Mars? Like, how big does it have to be? Because we also talked about micro lensing. It's just like, how micro is micro?
Very good question. So there is a bunch of things to start putting together in our minds now in order to understand the different territories of lensing. So the first thing is the geometry of the phenomenon. And you mentioned about, just before you mentioned the thickness of a lens. So, for example, somebody can wear very thick glasses or very thin glasses. They don't behave in the same way. There is something that, an approximation that we use in almost all flavors of gravitational lensing, except one, weak lensing, but this is the weird relative, let's say, the black sheep of the family, weak lensing. We will get to this eventually. Anyway, because the distances between source and observer and lens and the deflection angle from gravitational lensing, so the deflection angles are tiny and the distances are huge with respect to the thickness of your lens, we make an approximation that we call the thin lens approximation. This also happens in certain fields of optics. What do I mean by that? I mean that when you have a galaxy acting as a lens, galaxies are 3D objects. We know that they exist in 3 dimensions. But because their depth from our vantage point, so how thick they are from where we see them, is so tiny compared to the distance between us and the lens and the source, we can ignore the thickness and we can collapse the entire galaxy into 2 dimensions. And this is how we work now in 99% of flavors of gravitational lensing.
Yeah, and that makes total sense. I mean, that is a similar approximation that's made in tons of different scientific disciplines. You're just so far from the source, you can treat it as a point source or as a 2D planar wave, or
very, very correct.
It's a very common type of assumption. Given the distances, it becomes real and makes things easier.
Yes, exactly. Now, another important point to remember about gravitational lensing is that it's a very rare phenomenon. We talk about mainstream lensing now. We will get into the weird flavors later on, but the mainstream lensing is just two galaxies aligned, one 500 million light years away, another one 1 billion light years away. They happen to align in the same line of sight as we see it from the Earth, and this leads to this gravitational lensing phenomenon. So this is a rare thing. That's why it took us a long time to find the first gravitational lens. It was discovered in 1979, if I'm not wrong. This is why it took us a very long time to discover the next one and the next one and the first 10 and then the first 100. And we are now at around 1,000 galaxy gravitational lenses. And since the Euclid Space Telescope was launched a year ago or so, we have another 1,000. So Euclid is one of the instruments that will revolutionize the field by discovering many more gravitational lenses. It's very good for doing that.
Why is that? Why is it so good at finding these?
Very good question. When something is rare, you need to look throughout a big bunch, a big pile of things, a big haystack to find the needle, right? So Euclid is a space telescope that is designed to survey almost the entire sky. 70% of the sky. Hubble, for example, is a space telescope that was very famous, led to fantastic discoveries, but it has covered a fraction of the sky compared to what Euclid will do. Why? Because it was very powerful, but its field of view was very narrow, so it could observe only so much of the sky.
Okay. Well, that crosses off one of my other questions. So I guess I'll take one step forward and then go back. That means you have a two-stage process, I assume. You have Euclid, or other system like it, which is got that wide field of view that can find an event, whether that is where we're going with this micro lensing, or whether it's an Einstein ring, which we'll define later, or weak lensing. You find it with these wide field of views, and then you have a second stage where you zoom in with something like, not necessarily Hubble, but something like it, right?
Right. So the most easy to comprehend, let's say, way to understand how we find a lens, to look at an image and say, oh, that's a lens. The easiest way to understand this is when you have a big image of the sky, so you anticipate that there will be some gravitational lenses contained there just because of statistics, just because of probabilities. Then the second characteristic you need, or the second ingredient that your instrument must have, is high resolution. Why? Because when you have galaxy lenses, the separation between the ring around the lens and the lens itself is of the order of a few pixels on your camera. So if you're
that explains why it took so long to find them, right? Is because we needed that resolution. So even if we're looking right at one, we didn't have the resolution in 1970 to even see it.
Exactly. You just see it as a blob.
Yeah.
And when you improve your resolution, you suddenly see, oh, it's a lens, it's a galaxy, and around it, it has an Einstein ring. Oh my God, this is crazy. And by the way, this very nicely leads to a discovery made by Euclid that went public a few weeks ago. I don't know if this is in your agenda to ask me later.
It is. I figured now we're going to let everyone know the special sauce. Sometimes when we do this, I have no idea where it's going to go. I figured we'd start with the micro, get into the weak, and then leave the star of the show, pun intended, for the end with the strong lensing and talking about this particular instance. So we're jumping the shark.
Don't worry, this field is full of superstars, and there will be more appearing in the next few years. I hope, and I think I am convinced, but you always leave a little doubt as a scientist. So don't worry, there will be more coming up. So
Perfect. But maybe I'll interrupt you and I'll come back to it and finish up our micro lensing, because one of the things that I found in my prep was you can use micro lensing to find exoplanets. And I'm used to thinking of finding dips in the light as something transits across its star, maybe even using the spectrum of light to try to pull out a little information about its atmosphere, but a lens, micro lensing to find exoplanets, I was just blown away.
So very nice. You are very good in setting me up to describe yet another dimension of this phenomenon that will make more sense of what's going on. So because of my background, I have been mostly talking about cosmological lensing. What is that? It's basically lensing happening outside our own galaxy. And two galaxies lensing each other is such a case because they are outside our own galaxy, far, far away, and they do their thing, lensing one another. You can have gravitational lensing by any sort of compact object, be it a black hole, be it a stellar mass black hole or a supermassive black hole at the center of some galaxy, even our own. You can have lensing by a neutron star, you can have lensing by a common star, and you can have lensing by our sun even. You just need a source behind it and some nice alignment along the line of sight. And by the way, this was one of the major discoveries in 1916, I believe, if I'm not wrong, in favor of Einstein's theory of relativity. The theory was out, it was a crazy theory for its time, and people tried to confirm its predictions. One of its predictions was gravitational lensing. They had not such fancy instrument as we have today back then, so they had to make do with what they had, and they thought, look, if what Einstein says is correct, the sun, due to its gravity, should be deflecting stars that lie just along its rim, so very close to the line of sight, basically, to these stars. If the sun is somewhere there, then we could measure this position of the stars being lensed. They would appear as they're shifted a bit further away in a different position. And that, if we observe this, then we confirm the theory of relativity. It's one of the phenomena that it confirms. And it actually gave prediction for the number of degrees that this deflection should happen, the number of degrees that you would see a star move on the sky because of this lensing by the sun.
And they did this during a solar eclipse, right?
Exactly. Yeah. There was a huge problem of you have a bright sun sitting right there and you cannot observe anything around it. We didn't have satellites to go into space to do measurements like that back then. So they had to wait for a solar eclipse. They sent their teams. It was two teams. One went to South America, one went to Africa, I think. So this was just for redundancy in case one of them got bad weather. So there was a solar eclipse. They measured the position of a known star that was right next to the rim of the sun, which was now eclipsed by the moon. So you had no photons from the sun. And they measured that this star was shifted by the amount predicted from the theory of relativity. That was a fantastic discovery or evidence in favor of Einstein's theory.
Wow, I love those stories like that. And I guess that's a real good example of microlensing then.
Very close. First, we haven't defined microlensing yet, but we will get there. Now, back to this discovery with the eclipse and the moon being in front of the sun and us being on Earth. Do you know what somebody could claim? Somebody could claim, oh, you have the moon and you have a source behind it, which is the sun. Is the moon lensing the sun? And we on Earth could see the sun lensed by the moon? The answer is yes, the moon would be able to lens the sun, but we are probably not in the focus of that lensing system. So we don't see some ring around the moon, which would be the sun being lensed, or some deflection of the sun, something like this. We are not, right? You need the focus. The same way you have the analogy with your optical lenses, you need a focus to be able to see something. The same thing applies to gravitational lensing. If you have two galaxies aligned from our vantage point, if you go further away to some other planet on the other side of our own galaxy, maybe they are not aligned anymore. Or if you see them from another galaxy, these two are not aligned anymore, you change your focus. The focus is somewhere else.
I need to have another episode where I come back to all the funky things that the light does as the moon kind of starts to come across, because it does weird things with the polarization of light too and other stuff. But I think
I
that's
told you there
beyond.
is a lot of meat in this.
I
Field.
know. It's like the dinosaur episode that I did with T-Rex. It takes a lot of effort just to try to keep this on track, and because it's just so interesting. You just get so much fun even talking about it. That's why I started the
I'm
podcast.
very happy to hear this.
So wait, no, back up. You haven't actually told me what microlensing really is, because I interrupted. So let's go
Very
back
good.
there.
No, I think you didn't. So, what is microlensing, and what is its relation to galaxy lensing, or strong lensing, as we refer to this phenomenon? I was also trying to link this with what happens outside our galaxy, the so-called, what I called cosmological microlensing, and I wanted to make a distinction with what happens inside our own galaxy. So, what happens in our immediate neighborhood is lensing by the sun. We have seen this, as we said, with the discovery, with the confirmation of the prediction of the theory of relativity more than a century ago. Then, the most common way to use microlensing in the 90s and in the 80s was to try and discover planets in our own galaxy. How does this work now? We are entering a slightly different flavor of lensing now. Planets are stellar objects that do not emit their own light, so they are dark. You can only spot a planet in the sky, for example Jupiter, if you go out on a clear night, because it reflects the light of the sun. Now, for many, many years, astronomers were expecting that there would be planets throughout our galaxy. There was no reason. As soon as we understood that we live inside a galaxy and our sun is a star like the billions of stars in the galaxy, we were anticipating that these other stars would also have their own planets. But because these planets are tiny and far away, it's impossible to see any light reflected from the surface from their parent star, the star that they're orbiting, their sun. So it was impossible to observe them directly. You had to find a way to observe them indirectly. And people realized that, if such a planet orbiting around its star happens to pass in front of that star that we see from Earth, in other words, the orbit of that planet is in the same plane as our line of sight to that planet and its star, then when this planet passes in front, it could actually act as a gravitational lens. It will not be big enough to make an eclipse, let's say, an eclipse of some other star, as the moon was doing for the sun. That planet would be tiny given the distances to cause such an eclipse, but it could focus photons from its star, boosting the brightness of that star for some period of time, as long as it takes to cross in front of that star. And then 1 year later, but not a year on Earth, a year on that planet, which means one full orbit later, it would pass in front of that star again and magnify it again. And this is what people would use to detect solar planets. And one of the first solar planets were detected, not solar planets, extrasolar planets. So one of the first extrasolar planets have been detected in this way.
Wow, that's just awesome.
And again, this can only work in our own galaxy because we can see individual stars in our own galaxy, and we can detect tiny changes in their brightness due to this lensing phenomenon. In other galaxies, it's much, much harder to do this. They are too far away to perform this.
And just to reiterate something that you've already touched on probably already a half a dozen times, the alignment. I mean, the lens on my glasses, for that to work on Earth, I need to have it properly aligned on my face. That needs to sit on my nose, and I can adjust it, but I cannot adjust the cosmos. So these are really, really, really rare. And that's for the case for all gravitational lensing, not just microlensing, right?
Right. It's because the universe is a quite empty place, actually. So it's rare to have two things aligning with our line of sight.
All right. Now it's time to step out further and look to bigger things. Like microlensing is not the pinnacle of gravitational lenses. It's got micro in the name. There's also weak and strong lensing, which we've already mentioned. And I need a real quick deviation. I've always been fascinated by the choices of terms, even in my own field, super volcano, for instance. But in this case, we have micro, weak, and strong. Without looking it up, and I'm not sure I could find it, I assume weak and strong were measured first, and then eventually we could detect and measure the very fine scale for the micro, and they were just like, we've already taken weak and strong, so it's small, therefore micro? Is that like how the term came about?
You have half the story. Yes.
Half the story. Well, I deduced half the story.
So the first thing to realize, so let's start from weak. Weak is the weird relative. So we get back to weak lensing at the very end.
But that's the next stop, actually.
All right. Okay. But it's the odd one of the family. The other two are very similar. So what's the distinction between micro and macro or normal lensing? It's the magnitude of the deflection angle. That's it.
Okay.
So remember when I referred to galaxy-galaxy lensing, and you need a resolution of a few pixels on a detector to be able to see these two galaxies. So the one who is the lens, and it's the one that looks like a galaxy, and the one that is deformed around it. So the deflection angles there are of the order of an arc second. What is that? It's 3,600 of a degree. It's a very tiny angle. This is 1 arc second, but on the Hubble Space Telescope, on Euclid, or even James Webb's telescope, you are able to cover this tiny distance with a few pixels. So you have several pixels, a few tens of pixels, 10, 20, 30 pixels, something like that. James Webb has more pixels there. So you can resolve it, in other words. By the way, because we're talking about galaxies now, the phenomenon is not dynamic. It's frozen in time. Everything moves in the universe, but because these things are too big and too far away, these two galaxies move extremely slowly. So throughout our lifetime, they will stay there lensing, causing this lensing phenomenon. And maybe in a million years, they will have moved, one of them will have moved out of the way. So the thing would not be focused anymore, will not be aligned. So it won't be a gravitational lens. But as far as we are concerned here on Earth, they will remain a gravitational lens in that shape and form for our lifetime. No need to worry about that. Which is not the case when you have a planet lensing its star within our own galaxy. This happens dynamically, right?
Right. So I guess the story is that strong and micro were kind of postulated first, and then they just figured out weak, which is where we're going, and was like, what do we call it? And so I had it kind of reversed. Right idea, but reversed.
So a more rigorous definition between strong lensing and micro lensing is the magnitude of this deflection angle. So I mentioned that for galaxy-galaxy lenses, it's around 1 arc second. For micro lensing, guess how much it is? It's a micro arc second. So
it's a factor of...
It's a factor of a million smaller. So that's why you can also have nano lensing. When you have some even smaller in mass object, a small planet like Earth, the deflection angle it would cause to some star in the background or to some other galaxy, these things can also happen, would be 10 to the minus 9 arc seconds. To give you an idea of what this means, it means that when we observe a galaxy being lensed, we observe these multiple images and these arcs and all these kind of things because we can resolve them. A micro lens, which is a much smaller in mass, that's why it's causing this smaller deflection. So it could be a galaxy with 1 million times less mass, or some star or something like that. So a tiny object cause tiny deflections, and when it comes to micro lensing, it still produces multiple images, rings, arcs, and so on of the source, but this now happens in a tiny, tiny surface. In my presentations, I usually show a coin to the room, to the audience, and say this is the extent of the images produced by a micro lens. The extent of the images produced by a macro lens would be the size of the block, of the city block we are in, or of the campus that we are in having this presentation. So this is the distinction. It's exactly the same phenomenon, galaxy-galaxy lensing and micro lensing, exactly the same. It's just the scale that changes.
So now we're on to, I know it makes more sense to go strong, but that is the star of the show. So we're going to go to the weird black sheep of the family, the weak gravitational lensing. Now, maybe I should try my best at explaining it in my wacky way of trying to read everything all at once, and then have you correct me. Maybe we'll try something different. So my understanding is you take a whole bunch of different galaxies or a cluster, so to speak, a group of stuff in the same area of space, and you're looking for changes or slight deviations in the light that's coming from them, and you try to sum it all up to like the space of the whole area of all the individual different clusters, and try to model those deviations from what you would expect. And that is the lensing? That's my best. I'm sorry.
Yes, you're very close. So before we talk exactly about weak lensing, one important thing to mention about strong lensing is that it produces multiple images. This means that when you have a curved space-time, two photons that diverge from the source, so one goes, let's say, to the east, one goes to the west, they see this curvature in space-time and they both get deflected and focused onto the observer. And that's how you see two photons of the same thing coming from two different directions of the sky. You have multiple images. This is what we call strong lensing, basically, multiple images. Now, and this happens when you have a very close to perfect alignment. But if you don't have perfect alignment, what happens then? Your photons still get deflected because they feel the curvature produced by the lens, by that massive object, which extends further away from it. They get deflected, but you see only one image of the background source. And it's very hard to tell whether it was actually deflected or that source is actually right where it's in its proper position, not being affected by any sort of lensing. It's very hard to tell this. So one can think of that all the photons that reach us from everywhere in the universe, they have to pass more or less close to some concentration of matter, be it a galaxy, another galaxy, be it a cluster of galaxies. This is a bigger, in dimensions, a bigger concentration of mass, which means that the curvature that it produces covers a big area on the sky. So whatever lies close to that area of the sky, behind it, or near it, will feel that curvature and will be lensed, but without a multiple image. So weakly lensed. This is where we have the term weakly lensed. And
okay, yep. Now it's starting to make sense, the naming convention.
Yes. So weak lensing is a phenomenon that is very hard to tell whether it's happening or not. It affects, for example, the shapes of galaxies. So if imagine you have a cluster of galaxies and you have a bunch of galaxies around it feeling this curvature, but not being strongly lensed. So you have only one image of that galaxy, slightly deformed, there is a slight deflection on the photons that arrive from that galaxy to you. If you are able to measure the shape of these galaxies, you will find a correlation. If you think of galaxies as little ellipses, they will align in a tangential pattern, in a circular pattern, around the cluster that is causing this curvature. Like, for example, if you spread smithereens around the magnet, you see how they align and they follow the magnetic field. In a similar way, the shapes of the galaxies now will be deformed in a way to trace the matter, the curvature caused by the cluster in the middle. So we need to be able to measure shapes very well, and for thousands, millions of galaxies, to learn about the matter distribution in the universe in the largest scales. Clusters, filaments, the cosmic web, all these kind of things.
Oh boy, filaments. Wow, there's so much more to get into. I'm scared to continue digging because I know there's a lot more to go. But one of the outcomes of being able to do this is to look at the mass and the matter. But as anybody who's probably listening to this podcast already knows, there is matter we can see, and then there's matter which we can't. And we don't really know what it is, or at least I don't know what it is. It's dark matter is the way I've heard it. So these mysterious characters, I knew they would make an appearance here from the beginning. Perhaps it's time to talk about at least dark matter in the sense of like, they have an effect on the gravitational lensing. I mean, they might be the biggest culprit to them, right?
Exactly. It's the dark elephant in that room. Remember the dark room from before, the analogy with the dark room and the optical lensing happening in there? Now imagine that dark room is filled with something that you cannot see, but you cannot see that thing itself, but you can see its effect on whatever light you have in that room. This is dark matter. We know that 85% of total matter in the universe is actually dark matter, which means that every galaxy is made of 85% more dark matter than normal matter. All the atoms that we have around us, that we are made of, that shine, they give away photons, they are the normal matter, baryons. Dark matter is something that does not emit light, does not interact with light. The only thing it can do is curve space-time as well, the same way that normal matter does. So dark matter, the only thing it has in common with normal matter is gravity, and hence this bending of space-time. Therefore, it will cause lensing. And by measuring the lensing, let's say, the deflection angles, the deformation of galaxies, in strong lensing, in micro lensing, or in weak lensing, by measuring these deflections, we are measuring lensing by the total amount of matter. Then we point our telescope, or at the same time, we have pointed our telescopes there, and we see how much light we get from that area, which helps us understand the amount of normal matter that is there and its distribution and so on. So by contrasting the two, we can actually probe dark matter and how much of it is there, what's its shape, what's its form. There are very interesting things happening with different dark matter models. We are able to understand dark matter in the largest scales. This is the so-called cold dark matter paradigm. But in the small scales, and in the universe, small means the scale of a galaxy, cold dark matter, which works in the bigger scales, somehow doesn't work. There are some inconsistencies there. And this has led other theories to be developed, like warm dark matter, self-interacting dark matter, all of these things. And galaxy scales is the playground of gravitational lensing. And we can use this with data from telescopes like Euclid and others to be able to tell different dark matter models apart. And then we go to the laboratory and tell our particle physics colleagues, look, dark matter should be warm, or it should be self-interacting. Show me a model that explains this, and now you know what you need to go to the lab and try to measure, whether you can measure some interaction about dark matter. This is a whole story on its own.
Yeah, for sure. Maybe I just never quite appreciated how the two disciplines are intimately tied in that way, like particle physics and cosmology. Because, I mean, particle physics, you're looking at something so small. Cosmology, you're looking at it at such big scale. But at the same time, you're finding these properties and being like, okay, your model at a small scale, can you make it reproduce this? Mm-hmm. All right, this brings this part one of the pair of episodes on gravitational lensing. When we get back into part two, we're going to start with the star of the show, strong gravitational lensing and Einstein rings. Remember, if you haven't done so already, hit that subscribe button. Make sure that you're able to get every new episode as it comes out. Also, poke around on social media. Find me there. Make suggestions for shows. Give me feedback. Obviously, please rate the show. I want to make sure that more people can find it. All right. Till next time.
Lost in the fog of a cosmic storm, floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light, riding the waves that are just out of sight. In a world so chaotic that misbehaves, melodies that echo show us sex always. Colors intertwine, painting the sky. We're lost in the rhythm as the universe flies by. Oh, we're tuned in, feeling the beat of the unknown. Can you hear